It's my pleasure to introduce our first speaker, Professor Axel Scherer. Axel is the Natchez Professor of Electrical Engineering at Caltech, and he's very well known for many of his accomplishments. Among these, the first demonstration of vertical cavity surface emitting lasers. Many of you have seen these, his famous picture. It's like a nanoscale skyscrapers. Many layers of DBR mirrors standing several micron high and some micron width. And Axel has went on to make contributions in many different areas, including photonic crystals, silicon photonics, and in biophotonics area. And Axel also co-founded LUXTERA, a leading silicon photonics company, with Eli, and I'm sure we're going to hear a lot about that. So without further ado, let's welcome Professor Scherer.
Okay, it's a great pleasure to be here. I think with what I'm going to try to do is show you what we've done over the last decades, I think. I've known Eli since 1985 or so at Belcor. And what I'd like to show you is where we've gone from where we came from. I'm going to talk about photonic crystals, Silicon Photonics, and the company that Ming mentioned, LUXTERA. Originally, this was what I thought would happen. I worked on vertical cavity lasers in the 80s, and at the same time, Eli was working on trying to make three-dimensional dielectric structures. And I thought there was going to be a continuum. We would start with these one-dimensional structures, eventually go to two-dimensional structures. And then at some point, we would meet up with Eli and figure out how to make truly three-dimensional structures, and it would be very difficult to do so. But in fact, over the last couple of years, in the 1990s, we realized that actually, if we combined our efforts, we could make structures like this. And of course, this is one of Professor Noda's structures. We can make very high Q structures in a two-dimensional device, in a geometry. And what that means is it's manufacturable. And I think we came to that realization a little more than 10 years ago. And we thought about things. And so I'm bringing up this old view graph to cause distress to Eli. But basically, the idea was we could build systems that are planar, where electronics and photonics are integrated together.
I have to mention this one was for the sales pitch to the venture capitalists.
You can. So I dredge out old view graphs to irk Eli. Very interesting things are on here. So, for example, there's a solar cell that powers it. I love that. There are all sorts of electronics devices, and the only problem with this kind of structure, the only problem, was that it was built on indium phosphide, or it was going to be. And that meant that if we were going to do something together, I would have a significant part in trying to figure out how to make these things. And so to try to get out of that, we decided not to make it out of indium phosphide, but instead make structures out of silicon. And just about 15 years ago, a new technology came about to allow us to decrease the leakage currents in electronic systems. That was SOI, silicon on insulator, where you can have a very well-controlled, thin crystalline layer, perfect structure of silicon. And all we needed to do to make optical devices was to carve that up, make waveguides, and go ahead with our planar optical devices. So back in the old days, in 2001, we started LUXTERA with these people. These were all the co-founders, I think, of LUXTERA. Alex was the CEO. Eli was a visionary. Kerry Gunn was one of my students who had just started working on silicon, and these two undergraduates at the time were working on models, building modeling software. And we asked for money. And so, of course, we had to say, why now? Why would we do this now? It turns out the feature sizes of the semiconductor industry had just gotten to about 0.1 microns. 0.13 microns, that was the node in around 2001. And, of course, we believed we knew everything about the rest of it. So we could do the rest of it within this company, and within 2 or 3 years, we'd make lots of money. At least that's what I thought. It didn't work out that way, but there was a big need, actually, for high-speed communications. And if you look at this plot, it, of course, stops in 2001, because that's what we used for our pitch to the VCs, right? So what's interesting here is it shows the speed of the bus of a computer, the frequency, the data rate. And it compares it to the processor frequency at the time. And you see that, of course, you have the bus that was slower than the processor, so you would have these memory-starved processors. And the idea was, let's get something that changes this paradigm and increases, by using optics, the data rate. The idea was to build one of these chips. And, of course, Intel, in 2002, came to similar conclusions, that you must have some sort of optical interconnection system at some point. They predicted back then that these kinds of systems were going to be needed in 2012. And at the time, I thought this was tremendously conservative. Why we could build them in 2002? Why would we wait until 2012? But I think in reality, they were absolutely correct. They were looking at it from the market point of view. We were looking at it from the technology point of view. The whole point is to get rid of this kind of situation. Now, we had this idea in our VC pitch. We had to deal with coupling light. We had to deal with sorting it, with doing all sorts of modulation. And in 2007, LUXTERA started making its first chips. They started looking like what we had hoped for. And just last year, in November, they showed off their first 100 gigabit per second Ethernet chip, which allows you to have a USB cable, essentially, that works at that frequency. Astounding accomplishment, I think, in the last 10 years. And I have to say I had very little to do with it. I just happened to be there at the beginning. Eli's been, carefully monitoring things and moving things along. I've been just sitting, watching at the sideline, marveling at what happened with this technology. But I think the beauty of this is that our idea, our vision, has become a reality. That these kinds of devices you can buy now. In fact, I think LUXTERA has sold 1 million or over 1 million interconnects now. So the idea is that you have this electro-photonic system. It's based on photonic systems that were built by using CMOS fabrication. And then you add the electronics, and you have basically now this capability of integrating things on the same chip. And it's led to active optical cables and interconnects and things like that. 5 times lower power, 10 times larger scalability, higher reliability, and all of that comes along with silicon, with the silicon world. All these things are leading to this becoming, I think, a commercial success down the road. You can buy these things now. You can actually, this is what's in them. You have a laser source. You have these chips, the optical chips that I talked about. And they come in different lengths, and they come in different complexities with different speeds. And basically, I think it's a legacy that Eli has left. The newest devices, of course, the fastest devices will be essential, I think, in connecting supercomputers together and building essentially an optical backplane for the next generation of computers. What's really happening is the silicon world is continuously moving along. I'll talk a little bit about where we're going later. I'm going to sort of look at now what's inside of these devices, give you a very quick overview of what's in there before I talk about the future. There are waveguides. The waveguides are essentially index-guided structures etched out of silicon. The idea is, right now, people will need these systems in what we consider high-performance computers. Tomorrow, in the next couple of years, I think it will become more and more the gamers and the consumer electronics people that will need this kind of technology. So if you look underneath the hood of these chips, you basically see that there's a couple of different technologies that need to be there. I mean, it's basically for an optical transceiver process, you need a couple of different devices. You need a detector, you need waveguides, you need modulators, and you need some sort of connection system. And the connection system is actually, I think, one of the biggest problems that we had to face with at the very beginning of this endeavor. The problem is that the silicon waveguide looks like this. It's about 0.4 microns or so in size. And the scale of a fiber is, of course, much bigger. And you want to get all of the light from this fiber, or as much as possible, into this waveguide. And I think Eli came up with this idea that you would use a grating. I thought of tapers and other things. And Eli came up with this idea, which I think was really enabling the fact that you could make a grating, and this grating was actually not a periodic grating, but a designed electromagnetic sort of antenna to allow you to get light from the fiber to the chip. So this is a very early picture, again, coming from our VC pitch. Nowadays, of course, these gratings are extremely well designed, and you can get insertion losses down to less than a dB for a single mode of gratings, and you can even do two polarizations and connect them. Modulators, again, I think Eli had a big input in this, basically using the fact that silicon can change in refractive index when you change number of carriers. And all you need to do is make a MACH-ZEHNDER interferometer where you modulate one or the other path. And nowadays, these modulators are extremely well designed again, with very low VPIs and very fast speeds. And this was one of the first ones that we made, I think, in 2003, that could go up to 10 gigabits per second. We made some I think, at Caltech before we did this. I should sort of reminisce. And the fastest speed we could get to, the highest frequency, was 50 megahertz. Okay? And taking a very similar geometry and having it done in a real foundry, in a real fab line, made the difference between 50 megahertz and this 10 gigahertz. This is just data from them. So there's lots of capabilities inside of this. There's also detectors. You need to have germanium detectors. Again, it needs to be designed and optimized. These are avalanche photodiodes, and they work, again, very well. Germanium is up here. It's in the right geometry to minimize the capacitance for these kinds of systems. You need a light source. You need to have some laser. So all these things have been worked out. And it allows us now to have a technology that connects the electronics and the optics on a single chip. And so we can basically trade off the complexity between electronics and optics by taking this kind of approach of integrated optoelectronics. And before, I think we had to really make a stretch to make this argument. Now I think it's real. Summary is we have this very fast and very power-efficient communications technology that has come about over the last 10 or 12 years. Now, where do we go from here? I was going to spend just a little bit of time to talk about the future as I see it. Nowadays, the opportunity is that silicon has gone from where we were 10 years ago at 0.13 micron technology. It's gone down to the 32 nanometer node, and I think now is moving towards the 22 nanometer node. So the question is, what can we do next with silicon? Well, we could build systems that are taking advantage of that size scale. So we can build these kinds of systems ourselves. We can ask Intel to do it or other people to do it, but we can do it small areas on our own. And we can make structures that are now down to about 10 nanometers in the lab. Okay. This is where we are today. 2011, I guess that was last year. We're on the P1270. I don't know what that means. But basically, it's a 22 nanometer technology. Okay. And we're going to, in 2015, be at the 10 nanometer technology. And I used to never trust this, but I do trust it now because these people are professionals. They know what they're doing. After all, Intel has told us that in 2012 we'll be selling optical cables, and they were correct. So I'll trust them now. The kind of transistors that we build are basically more and more three-dimensional. Okay, that's because of the way that the silicon scales. It's fully depleted. You need to put carriers in there somehow, so you need to have gates. So you could build structures that look like this. This is 50 years technology now, scaling this device down to smaller and smaller dimensions. Or you can change something. You can maybe make things that are vertical in nature and quite interesting, actually. Again, we can build things now in our lab, in small quantities at 10 nanometers. But we don't have to, actually. It turns out that we can cheat. When we make these kinds of structures, we see that they change quite a bit. So they're just purely mechanical properties of silicon changes. That's sort of an interesting observation, because if you look at, for example, this thing, there's a little ablated piece of dust that gets irradiated by the electron beam. It pulls with it these silicon whiskers. You see, this whisker is almost pulled perpendicular to its original shape. And then in the next frame, it's perfectly straight. It's purely elastic deformation, and you can get 25% elastic deformation in silicon without it breaking. So it looks like rubber. You can make devices even smaller than their original size by simply oxidizing the silicon. That's the beauty of silicon. You oxidize it, make it smaller. You actually integrate the oxide as a way to passivate the surface, and you can also use it to strain the silicon. So you can make a tensile strained silicon this way. It's very interesting. It doesn't break because it has this very small structure and elastically deforms. And you can make these structures actually quite easily down to 2 nanometers in size, okay, by oxidizing down bigger structures from silicon that you make 20 nanometers or more in size. In fact, you can dial in how wide you want to make them simply by choosing the temperature that you oxidize at. There's the viscoelastic limit, and it basically, the oxidation process terminates at some point. So one of the interesting observations is that you can start doing photoluminescence on silicon when you make structures that are that small. Silicon starts becoming more and more direct in its band structure because of the geometry and the strain. And you see that if you change dimensions from 8 nanometers to 2.5 nanometers, you get a blue shift that corresponds to what you would expect. Now, in 2 dimensions, you can etch silicon really well. Now, this is not a particularly good etch. It's undercut, as you probably noticed. But what you can do is you can change your etching conditions to recover the undercut and make a dimple into the silicon. You can actually do this in many times. You can make a corrugation, or you can make things that you would consider quantum dots in silicon simply by changing the etching conditions to make a three-dimensional structure out of a two-dimensional template. You do this by doing the etching process. And in fact, if you make these quantum dots, you can differentiate through photoluminescence between a 2 nanometer and a 2.5 nanometer wide quantum dot. Measure it. And you can make transistors. We're thinking about making these kinds of structures that are multi-gate transistors now, because the silicon is fully depleted, so you need to inject things. The neat thing is you can make a MOSFET, an N-channel MOSFET, into a P-channel MOSFET simply by changing the bias. I think there's a great opportunity there to go even further. I don't know where it'll lead, but I was going to look back, see where we've come from, and I was amazed. Compared to what I thought would happen 10 years ago, I had very modest expectations. Compared to those, I think the last 10 years, the work that people have done, and this is certainly not my group, but it's mainly done at the commercial level at LUXTERA. I think it's mind-boggling, and it gives me great enthusiasm to look in the future. Thank you very much for your time.
We have time for some questions. Tom?
Can you comment on the defect density of the silicon oxide interface in your silicon pillar structures?
In the pillars, yes. Yes, that's a comment. The comment is, I will give yes. It has lots of defects, a lot of more defects than you would have in a flat surface at a MOSFET. Having said that, the good news with these kinds of devices is that they tend to have attributes. For example, their threshold voltages tend to be extremely low, and they have opportunities that maybe differentiate them from the conventional MOSFETs that have been carefully designed over the years. I think the biggest argument for using these kinds of sized structures at the moment is that you could build systems that could be quantum mechanical in nature. You could build systems that probably would take advantage of the electron coherence. So, for example, you could imagine building a double barrier structure where you then build a tunnel diode. And you can do this out of silicon without having to use multiple materials. You can use geometry to change the relative size and therefore the band structure of different regions. That's at the expense of having a not so good interface because of the different crystal planes that you have to deal with when you do the oxidation. So it's a very good point.
Okay. Well, Eli, you want to ask your question?
Well, actually, more of a human interest. On one of your slides, you showed pictures of the founders of LUXTERA, and maybe you can just tell us where they all went, because I met Mike Hochberg on Wednesday at the Photonics West meeting.
Sure.
And
yes.
He has a very interesting story. Maybe just tell us the story of what became of the founders.
Yeah, so let me bring back the old view graph, because it puts the names with a picture. Alex started another company with me in the biomedical area. We sold the company. We were both very happy. I'm still at Caltech. I haven't improved. Eli, of course, has done better. Kerry Gunn started a company called Genolite that's using silicon photonics to measure antibody binding reactions and things like that. Michael Hochberg is a professor at the University of Washington, and so is Tom Bear-Jones. So they've made their own careers They were
I should
undergraduates.
mention they're just, both of them are in the process of moving to the University of Delaware.
That's true, yeah. So they're just moving.
And Michael is sort of become nationally known. He wants to convert the silicon photonics into a foundry technology that all universities could get access to.
Yeah, it's a new effort called OPSIS, which I hope is going to be successful because we'll all benefit.
Okay, let's thank Axel again.